Hello class, this is CSE-5250, section 60, week 5, fall 2023. For this week, I would like to go over 3 things. The first one is a little bit of help on how you can write your random number generator for one of your programming assignments. Programming assignment has part 4, which calls for a program that calculates the number pi using random dart throws. So that's part 1. Part 2 is what you'll eventually be writing for your midterm project, because we don't have exams in this class, we have projects instead. Part 3 is a brief look at how we can start programming programs where instead of OpenMP, it's pthreads. Alright, so let's begin with our random number generator. Probably better if we just start with the code itself. I do have a PowerPoint that more or less explains everything that I had, so you can look at that as well, but I feel like it's better if I just have the code that we can not only step through together, but run together. So, typically, when we have an application that requires a random number generator, we include, among other things, time.h. This is to access a function called time, and we need that later on. I'll explain that a bit. But typically, when we have a random number generator, we would have something like this. We would have srand time null, and then we would have something like this. Typically, with a random number generator, we have srand time null, and then we can call the rand function, rand left parenthesis right parenthesis, and that's how we can call random number generators. That's how we can set up a random number generator and then create random numbers. One other thing that you may have seen is, well, this random number generator, this rand function, will create a number. It's just going to create a number. Technically, it's going to create a number between 0 and the largest possible value it can ever create. That number is 21474834647. So, like, 2 billion. 2 billion something something. So, we want to constrain the range in which this random number generator generates numbers like this. If we, for example, wanted a random number between 1 and 10, we would need to do rand mod 10 and then add 1 to it. So something like that. And this would produce random numbers between 1 and 10. And if you want, say, a d20, there you go. Now you can generate numbers between 1 and 20. That's typically how it's. That is the typical process for random numbers, for generating random numbers. But these are integer values. I'll get into a bit on how we can get floating point values. But first things first, what would it take to make our dart throw program? Well, consider this. Our program is going to be throwing darts at a dartboard, but we don't want to throw one dart at a time. We want to throw a whole bunch of darts at the same time. So we're throwing a whole bunch of darts at the same time. But more specifically, each thread is going to be throwing its own dart at a time, but at the same time, it could be multiple threads throwing their own darts at the same time, at the same dartboard. we want to make sure that each thread has thrown, its own dart randomly. So one way we can know that has happened is to make it so that each thread has its own random number generator, and they each have its own seed. So here I've erased the code for our other random number generator. Here's how it works. We enter our parallel section with pragma OMP parallel, num threads thread count, and then private seed. We get the thread ID by calling OMP get thread num, and then we call time null. So what time null does is time null seeds the random number generator. So it seeds srand with the number of seconds since January 1st, 1970. This is how a random number generator works, at least for our purposes. You can think of it as a complicated function that, when given a starting value, we call that a seed. It's then going to generate, every time you call rand, it's going to generate a random number each time. So if you called rand 10 times and you got 10 different random numbers, and then you ran the same program to get 10 random numbers again, it's going to be different each time, because when we call time null, that program is going to be called at a different time than before. That means the seed is going to be different. Therefore, it's true that we can get different numbers every time we call the program. Such random number generators are called pseudo-random number generators because they depend on a seed. They depend on a seed value, so we say these are deterministic. If you want a real random number generator, like a true random number generator, you want something that's non-deterministic. You want something that doesn't require a seed at all. However, with such random number generators, you typically need a source of randomness, such as looking at the sky for atmospheric disturbances, or staring at a wall of lava lamps. But for our purposes, this random number generator, this pseudo-random number generator, is good enough for our purposes. It wouldn't pass the scrutiny of, say, cybersecurity, but we're not doing cybersecurity with this anyway. So we can get away with using a pseudo-random number generator and then use that information to throw a whole bunch of darts at the wall. So, back to our parallel section. We call OMP get thread num to get a thread number. Then we call time null to get the number of seconds since January 1st, 1970. We add them together, and then we have that value be our seed. That way, even if by coincidence every thread in our program started running at the same time and they each got the same value returned by time null, by adding the thread ID, we have it so that even then every thread will have a different seed. So when we call rand for the first time, every thread will generate a different random number. So how's it that we're getting how's it that we can get doubles, like floating point values, out of a random number generator? Well, here's how. Obviously, we need to first seed srand with the seed. That seed was time null plus the thread ID. But once we're there, we call rand, and then we do floating point division with rand max. because rand is going to return a integer value, but we want it to be a floating point value between, say, we want it to be a floating point value. So the first thing we need to do is divide rand by rand max. Rand max is, depending on the system, it's going to be 2,147,483,647. So if we divide rand by rand max using integer division, we won't get anything. That's why we want to cast one of these values as a double. So that way floating point division takes place instead, and then we'll get a floating point value between 0 and 1. If we want a value between -1 and +1, our next step is to multiply that number we just got by 2, and then subtract 1 from the product. So that's what's going on with this. This whole line is generating a random number between -1 and +1. So if we were to run this program, I'm gonna do Control-Shift-B to build the program, and then I'm gonna move my face cam out of the way so you can see me right-click on the solution, open in File Explorer, navigate to my debug folder, and then there's our executable. What we want to do next is type in PowerShell into the address bar, and then we type in our command to run the program, which is /name of the executable, and because the program has command line arguments that it needs to take in, we type in, say, the number 4. When we run this program, take note of this. We have a parallel section, but the for loop doesn't have a parallel for. It doesn't have OMP parallel for. No, pragma OMP 4, I mean. This is because we want each thread to generate 10 random numbers each. We don't want the program to generate 10 numbers. We want each thread to generate 10 numbers. So when I run this program, thread 1 has produced the random number -0.0444 as its first value, and then thread 3 has -0.0446 as its first value. Thread 3 has -0.0440. Thread 2 has -0.0442. Those sound pretty similar, but then it starts to diverge once we get to the last numbers. Check this out. Thread 1 has its last number be 0.1991. Thread 3 has its last number be -0.5514. 0 has 0.5744, and thread 2 has -0.1761. So we have our random numbers. Or rather, we have each thread generating its own set of random numbers. So this is one thing that might happen when you are doing your dart throw program. You might have it so that the number of darts you're throwing is dependent on the number of threads you have. So if your program calls for like 1,000,000 dart throws, but it's like 1,000,000 dart throws per thread, and you called it with 16 threads, that's what? 16 million dart throws. So you may need to do some integer division to more properly divide up the work. So this is just a consideration to keep in mind for when you have random number generators, but for a multi-threaded application. Oh, you may have also noticed that during this whole time, I also had a PowerShell in here. So how did that happen? Well, first I'm going to close it so I can show you the whole process again. How did we get a PowerShell over here? Well, if you go to View, click on Terminal, and then you'll get a developer PowerShell. This is going to open in some directory. That directory is going to be, if I can move my face cam, I can open folder in File Explorer, and it's going to be, that PowerShell is going to open in this exact location here. So we can use this PowerShell, or we can use this one. It doesn't matter because it'll more or less do the same thing, just in different ways. Okay, so we build our program. We do ls to see where we are, and we're in the folder that has our debug folder and our solution file. We do cd debug, and now we're in our debug folder. ls to see what files are here, and we have our executable. Perfect. I'm just gonna copy paste. That's Control-C has a different use here, so we can't really copy paste. I'll clear that. ls again. So now all I gotta do is type in our command at /. The name of our executable is CSE-5250 underscore OMP underscore RNG.exe, and then I want to type in the number 4 after that. And look at that. We have the same thing as we had with this PowerShell. But of course it's going to be different because we ran it at a different time, so all the numbers are different. But all the numbers are different between each thread. So we got it. Okay, so that is the basics for how we can create a multi-threaded random number generator, if you can call it that. This is just a start for your Monte Carlo pi estimation program. If you would like to know how to create random coordinates, all you really got to do is call this twice and then store the 2 random numbers as our x and y coordinate. And that's it. Anyway, actually there is one other thing. If we went in and added back our Pragma OMP4, we built this program again. So this way, it is going to generate 10 random numbers for the whole program instead of 10 random numbers for each thread. If we run this program again with that modification, then it's going to generate only 10 random numbers across the whole program. So what this ended up doing is threads 0, 1, 2, and 3 will generate their own random numbers, but they're still generating them with their own seed values. So that thing I said about how we have the number of darts being thrown being influenced by the number of threads we have, that might not be an issue after all. So I guess this is another starting point for your dart throw program, on top of calling this twice and storing it within 2 values. In fact, to drive the point home, rand x, rand y, I'm going to modify the program like this, and %.4f, and then rand x, rand y, save, rebuild, rerun the program, and there we go. Now we have not random numbers anymore, we have random coordinates. All that's missing is a means of determining whether that number, those coordinates, all we gotta do is determine whether those coordinates are 1 unit away from the origin or less. And basically we have the entire program already. Of course we need the counter still, but still. This is basically like nearly half the program already. What do you know? Alright, so that's part 1. Let me pause the video so I can grab some other materials and... Alright. So this is a preview of what I'm going to have you do for your midterm project, as well as your final project. It's going to be based on the same program, and that program is going to be the sieve of Eratosthenes. This is a program that finds prime numbers. So I have the Wikipedia page pulled up that not only has an animation of the whole program and the whole algorithm in action, but it also has pseudocode for the entire algorithm here. So, how it works is, well, I also have a presentation for this. So, this is from an older class, but maybe I can adapt this for this class as well. So, let's say we want this to find all the prime numbers between 1 and 50. First, we need to skip the number 1 because that's going to screw things up if we did it. What this is going to do is it's going to start at, say, some number and then cross out multiples of that number. So if we had the number 1, it's just going to cross out all the numbers. And then we wouldn't have any prime numbers left, and then we would conclude that there are no prime numbers. That's not how it works. So here's how it works. We skip the number 1. And then, since the first number in this list is actually going to be 2, we go up by 2's and then cross out each number we encounter. So we cross out every other number, starting from 2, but not including 2. And then we go to the next number that we haven't crossed out. That's the number 3. We go up by 3's and then cross out every number we see. So 3, 6, 9, 12, 15, 18, 21, 24, 7, 27, 30. Some numbers will have already been crossed out because they were also a multiple of 2. Don't worry about that. And now we go to our next number, 5. That's the next number that we haven't crossed out because we have already crossed out the number 4, so we don't have to worry about the multiples of 4. If anything, the multiples of 4 contain some of the same numbers as the multiples of 2. So by crossing out the multiples of 2, we've already crossed out the multiples of 4. In a similar vein, by crossing out the multiples of 2, we've also crossed out the multiples of 6. And by crossing out the multiples of 3, we also cross out the multiples of 9. So 4 we skip because when we were crossing out the multiples of 2, we have already crossed out the multiples of 4. So our next number is actually 5. We crossed out all the multiples of 5. We go to the next number. That number would be 6, but it's crossed out already. So really our next number is 7. Then we cross out every... And then we would cross out every other number... No, every 7th number as a multiple of 7. So, there is actually another trick. If we were to keep going, and we would then go to the next prime numbers, that would be 11. And then we kept going to the number 13, and then 17, and then 19, and then 23, and then 29. Well, what happens if we were to cross out the multiples of 29? The number 29 would actually be past the halfway point of this example. See, 25 is the halfway point in our example. 29 is like way past number 50. That is what, 58? So if we exceed the midpoint in our list, then we don't have to keep going. But there is another trick that is due to math reasons, and that is because we don't have to stop at the halfway point. If we have a list of, say, n numbers, we just have to stop at the square root of n instead. So the square root of 50, well, the square root of 49 is 7, so our stop value is going to be something between 7 and 8. So actually, in this example, all we had to do is stop at the number 7. And then from there, any number that we haven't crossed out, that's a prime number. So that's how the sieve of Eratosthenes works. I don't have a slide for this yet. I will need to adapt it for this class. This is from when I taught this class in the past. So, if you want a head start on how you can program the sieve of Eratosthenes, keep in mind we need to program it as a serial program first. So, I will tell you right now, there is a doubly nested for loop. So there's a nested for loop in here, and the pseudocode here has it. We have here a nested for loop. We have a for loop and then another for loop. I will also give you one other hint. We can only parallelize the inner for loop because the process of crossing out multiples of a prime number, if we can do two things in any order, then we can do them at the same time. That's the rule that we have for parallelizing code. So, if you were to go back to, say, crossing out the multiples of 2, it doesn't matter whether crossing out the 4 will affect, say, crossing out the number 10. It also doesn't matter if I do them in the backwards order or any order, as long as I know I'm crossing out the multiples of 2. I can do modular arithmetic to make sure that I am crossing out the right number. So if I land on the number 13, I can just do some modular arithmetic. Divide it by 2 and see if the remainder was 0. If the remainder was not 0, ignore that number. That wasn't the right number. But if I do modular arithmetic on the number 12, I divide it by 2, I get a 0 remainder. That is a multiple of 2, cross it out. So it doesn't matter in what order I cross out all the even numbers. Therefore, I can cross them all out at the same time. So that's the part of the program that we can parallelize. We cannot parallelize the outer for loop because, as shown in chapter 5, that means we have a loop carry dependency. The outer for loop is concerned with finding the next number that hasn't been crossed out. So it's 3, and then 4, but that's crossed out, and then it's 5, and then 6, and then 7, then 8, and then this is why we need that outer for loop. Otherwise we would be redundantly crossing out numbers that should have been crossed out. So when we do the multiples of 3, it's also going to cross out the multiples of 9. So that way, when we do the multiples of 3, if we're doing this for a large enough list where we have to consider the multiples of 9, well, I'll just tell you right now, we will never have to consider the multiples of 9 because by crossing out the multiples of 3, we also cross out the multiples of 9. So, because in the outer for loop, the next for loop iteration depends on the previous for loop iteration, we cannot parallelize the outer for loop, but we can parallelize the inner for loop. So that's one thing we can do. Again, if you want a head start, you can turn to, say, the pseudocode here and then turn this into a C program. You would need to make an array of numbers this one uses an array of Boolean values. That also works too. You just have to convert the index into a prime number. The outer for loop goes from the number 2, but it can't exceed the square root of n, where n is the number, where n is the length of our array. Yeah, so this is one way we can actually program the sieve of Eratosthenes. When we get closer to doing our midterm project, I'll give instructions for you then. But if you want a head start, well, here you go. Alright, so that's part 2. Part 3 is our start on pthreads, and I'm gonna have to switch gears again, and I'll be right back. Now, before I continue with the presentation for pthreads, there is one other detail I should mention. The ultimate goal of our midterm and final is to see whether parallelizing a program reduces its execution time. So, yes, we're going to be writing the sieve of Eratosthenes, but at the same time, we want to time how long it takes to run. Not just for however many threads we have, but also how many prime numbers are we looking for. So if we're, say, looking for prime numbers up to, like, say, 1,000,000, we're going to have an array that's of length 1,000,000. But if we have, like, say, 16 threads all working at the same time looking for prime numbers up to 1,000,000 using that sieving process I described. So if we were crossing out the multiples of 2, then each thread is, for example, each thread is crossing out a different multiple of 2. And each thread would be working at crossing out a specific non-prime number. So we use our team of threads to parallelize the inner for loops, the inner for loop iterations, but not the outer for loop iterations. So, with that information, can we say that we are getting a speed up by using OpenMP? At the same time, is there a workload for which we can say that parallelizing helps, but at the same time also, how many threads is too much? I talked about Amdahl's law, and one thing that can happen with parallelizing programs is that you're going to get diminishing returns. So, eventually you'll also be answering the question, is there a sweet spot for the number of threads for the sieve of Eratosthenes? But all of this is for a later date. Once again, if you want a head start, just write the sieve of Eratosthenes as a serial program. No parallelization whatsoever. We are going to be using OpenMP as our means of parallelizing the sieve of Eratosthenes. But for now, we're going to switch over to pthreads and see how that works. Right, pthreads time. So this is all chapter 4 of the textbook. So here we have our Hello World program that uses pthreads. I modified this from the textbook because the textbook has a few things that don't work. So I'm going to explain the modifications as we go along. Also, this code is spread between 2 slides. So we have lines 1 to 36 and then 37 to 44. So if you want to recreate this program, keep in mind it's spread between 2 slides. So here's one of the first modifications. In the textbook, it was using a long as the data type for thread here, and also rank here. But to make sure there wasn't any ambiguity over what long meant, because in some systems, int is 16 bits, not 32 bits as we might think it is. Long int is 64 bits. Or at least it should, or at least that's what we think it should be. But to make sure there's no ambiguity at all, I went in and included standard int.h. And I used the data type int64 underscore t instead of using, say, long int. But you can use this with long int. Just be mindful that it might be dependent on the platform. So yeah, that's the first modification I had to do. So let's step through this code. Okay, so say you go in and write the program as it's written here. Yeah, I said it was the first modification, but it's really the only modification. The other modifications were error corrections. So let's say you go through the process of writing all this code out and you want to compile it. Well, on Unix systems and Windows machines that have access to the GCC compiler and Windows PowerShell, you'll want this command, gcc-g wall-o, filename.c, and then lp thread. On some systems, you might not need the lp thread, but this is the command that you'll be using to compile your pthread programs. And that's it. The next couple slides are specific for a Windows system. So if you have access to, say, Visual Studio 2019 or Visual Studio 2022, go to View, click on Terminal. You'll get a terminal, you'll get a developer PowerShell in the same place as you would see your error list. You can use all the Linux commands as we normally would. Excuse me. I got alarm clocks all everywhere, so don't mind that. Okay. We have our developer PowerShell. We can use all of our Linux commands, such as ls. So we can use ls to determine where we are in our folder. So when we start up this PowerShell, we are in a project folder called CSE-5250-60. What we want to do is, it turns out there is another subfolder with the same name, so we have to do cd and then CSE-5250-pthreads. So that's why in this next slide, this is our current directory, CSE-5250-pthreads / CSE-5250-pthreads. After we do that, we're gonna want to find our CPP file. And it is in that subdirectory with the same name as I just said. So we have to navigate to a subdirectory that has the same name as our current directory. It's in there that we'll find our CPP file, or a C file. This is specific to Windows and PowerShell. Visual Studio, Windows, PowerShell combo. And then we can use our command that we had here to compile our program. And then we can run the program doing / name of the program and then number of threads. I'm gonna break out of the presentation here so I can head over to Visual Studio and show it to you. So here, we have the same program again. And all we gotta do is click the local Windows debugger, right? Well, if I did that, build failed. And that's because Visual Studio doesn't know what a pthread is. Cannot include file pthread.h. No such file or directory. But if you're on a Windows system, and your Windows system needs to have the GCC compiler on it. So if I type in PowerShell, for example, and just run PowerShell, if I have PowerShell and just type in GCC, it's gonna say fatal error, no input files. That means I have GCC on my computer, and it didn't work because I never specified an input file. That's our C compiler. On another topic, if I did G++, that's our C++ compiler. So I have the compiler already on my computer, so I can proceed with the instructions that I have here. So exit. So here's the code that we have from before. You can also do this on, say, the lab machines in Jack Brown Hall by either going to the lab in person or possibly remotely. If you need instructions on how to remotely access the lab computers in Jack Brown Hall, then I'll post the instructions then. But for now, let's proceed with compiling this program using the instructions that I gave out here. View, terminal. Now we have a developer PowerShell. ls, this might be a little hard to see, so I might have to zoom in. This might be a bit tricky. So, let's see if I can zoom in. Hope this works. Right. ls, and we have another directory here called CSE-5250 That's just the name that I gave to the whole project. So I'm going to do cd CSE-5250 pthreads, ls again, and there we are. We have our CPP files. So if I wanted to compile the command, I can just write in the compile command. I have already written it down, so that's why I was able to pull it up that way. I used the up arrow key to pull up previous commands that I typed out. Here I named my executable a different name so that I don't have to type out the long name again. But anyway, gcc-g -wall, no, I think it was just wall, not dash wall, -o, name of the executable, name of the source file, and then -lp thread. If I type all that in, then it's going to compile, and now we have our executable. If I type in ls again, then there we go. I already had the executable, but if you look at the timestamp, it's different, so that means the program was able to compile successfully. Okay. So when I run the program, what happens? /pthreads. If I just type it in by itself, just /pthreads, it's gonna say hello from the main thread. So it's a little bit different from when we had the OpenMP Hello World program. But I guess this difference is more pronounced if I said 4 threads, run with 4 threads. And now we have hello world from thread 0 of 4, 1 of 4, 2 of 4, and the 3 of 4, but also hello from the main thread. We have 5 threads when I typed in 4. Why is that? Okay, so let's step through the code itself. So let me just fix my screen a bit. There we are. Shrink this down and let's look at the code together. In fact, it might be better to just look at the PowerPoint slides instead. So we start off with our headers, our include headers. So we need pthread.h as one of our libraries. We also need a global variable called thread count. In OpenMP, we had a function that would give us a thread count, but in pthreads, for us to fulfill the same thing, we need a global variable called thread count. We're going to assign a value to that later on. We also need a function prototype for our thread function. We'll look into that a little bit more. When we get to our main function, we need that to take in command line arguments. There's that thread value again, but it's of the data type int64t, or it can also be long int. So we are using this strol function to get our thread count as a command line argument. But look what we have between that and int64t thread. What's this pthread thingy anyway? Well, that's a pointer to our thread handles. So what is this pthread t? What is this pthread t thing anyway? Well, this is a data structure for storing thread-related information. It's what's called an opaque object because the data that it's on is not only is that information not accessible to the user, it's also system specific, so it's called an opaque object. But what are we doing with this pthread t thing, this thread handles? Well, it's our thread handles. But more specifically, we need to allocate space, we need to allocate memory space for our thread handles. So, however many threads we have, in our example we had 4. We had 4 threads, but we need enough space for 4 of this pthread t. So, we do thread count times size of pthread t. We have the malloc function for allocating memory, and we give it that size of thread count times size of pthread t. That's how much memory we're going to be allocating. Also, you have to cast this to pthread t pointer. And that is our thread handles. So thread handles is a pointer to our pthread t data structures. And now we are at the part where we're starting to fork our threads. In OpenMP, the system would fork into a team of threads. And if we had 4 threads, the main thread is thread 0. It would create 3 more threads with the IDs 1, 2, and 3. Here it's a little bit different with pthreads. So when we create our threads, we have the function pthread_create, and it has 4 arguments. The first argument is a pointer to the thread handle for that thread. So that's why it's address thread handles and then thread in square brackets. The second argument, just leave it as null. The third argument is the function that we want for our function to run. So that's going to be the hello function. We've seen this a few slides ago, and it's this one. So that's our third argument. The fourth argument is a pointer to the argument to be passed to our function. So void start thread, well, cast to void start thread, if we go back to our thing here, we have void star rank as our parameter, but we want to pass an argument to our hello function, and that argument is going to be thread. So what's going to happen is each thread is going to call this hello function here. And it's going to be given the thread ID as an argument. So that way, when each thread runs the hello function, it's going to say hello world from thread %LLD of %D. That means hello world from thread ID out of however many threads we have. And thread count is our global variable. So that's why it's there too. So the main thread creates 4 threads. But in OpenMP, the main thread would be part of the team of threads that it would create. Here, in pthreads, if we say we're making 4 threads, we're making 4 threads on top of the main thread. So that's 5 threads. If this was back in OpenMP, if we want 4 threads, the system would create threads until we had 4 threads. So we'd be creating 3 threads. Here, in pthreads, we are creating 4 threads, and then the main thread gets to do its own thing. It's going to say, the main thread is going to say, hello from the main thread. And then the other threads do their own thing, where they each say hello, until each thread finishes their execution. They finish execution, and then what? Oh yeah, another thing. With pthreads, there isn't a way of assigning threads to CPU cores. That's a task that's typically done by the operating system. In the worst case scenario, many threads may end up sharing the same core, but if there's an available core, the operating system will say, here, take this core, you'll need it. So what's this pthread join? Well, remember the fork and join model from before, where a system would fork into multiple threads, and then those threads would later join back with the main thread? Well, we're seeing that fork and join model here again. When we call pthread join, and we pass it the thread handle, basically that says, wait for this thread to join back with the main thread. So when we call thread handles for, when we pass in the thread handles for, say, thread 0, the program's gonna wait for thread 0 to finish executing. Well, thread handles 0, or I guess more generally, thread handles thread, it's going to, when this for loop is called, it's going to wait for every thread made using pthread create to finish executing. So the first argument is the thread handle, then the second argument, we can just leave it as null. Oh, and at the absolute very end, we need to free up memory that we used for our thread handles. Otherwise, we're going to end up with a memory leak. Because we allocated memory previously for our thread handles, we need to free it when we're done. Otherwise, you get memory leaks. Similarly, when we create threads, we have to make sure, when we fork threads, we have to make sure they join back later. Otherwise, we get this, zombie threads. If we fork and forget to join, then we end up with zombie threads. All these things do is waste resources, and they may also end up prevent the creation of new threads. The thing is, sometimes you want a thread to go on its own and then finish on its own time. The main thread shouldn't have to wait on that one thread. So in such cases, you may want to detach that thread. maybe we'll look into that later on. So that's the step-by-step process of how this program works. It's the fork and join model again. The main thread forks into a bunch of threads. Each thread does its own thing. The main thread waits for those threads to finish, and then they all join back with the main thread. That way we don't have zombie threads and we aren't wasting any resources. In terms of error checking, it would be a good idea to determine whether we typed in a valid command line argument. So, I typed in 4 for our command line argument. What if I typed in AAA? That wouldn't work. That's not a numeric value. Also, did you know that those pthread functions return an error code? It might be a good idea to see what those error codes are, just to make sure that we have nothing going wrong with our program. Or put it another way, just in case we have something going wrong with our program, we can see what those pthread functions were returning, and then we can determine what kind of error is happening. So what I just showed you was a program that would fork and join its threads as needed. What if this was all happening in a for loop? So, what if I say, what would happen if, for example, I put all of this code here from lines 22 to 30 into its own for loop, so that way would it be lines 22 to 30 or possibly the stuff before it? Anyway, what if I had a for loop where I had to fork and join threads again and again and again? Well, here's the thing. There is overhead with starting up threads and joining them back with the main thread. And that overhead adds up really quick. So what if there was a way where I fork and join once and I use threads as needed? In game programming for example, we have a similar thing. It's called an object pool. So here you create like 1,000 cars and you just put down cars on, say, a road to drive on as needed. When those cars are finished driving on the road, the video game engine will just take those cars back, put them back in the pool, and those cars wait for when they need to be used again. We can do a similar trick with threads, and that is called a thread pool. So we create a collection of threads at the start of the program. Those threads wait for work. The system will take out a thread from that pool as needed. It's going to assign work to those threads. Those threads do the work, they finish the work, and instead of joining back with the main thread, they just return to the pool and wait for more work. Now, this could also be wasteful if you end up allocating way more threads than you need. So here, it sounds like a balancing act because, well, it is. You have to balance how many threads do you need at the same time. Yeah, you have to balance. Yeah, it's basically balancing how many threads you need for your program. If you allocate way too much space, for example, that's bad because that's wasted resources. At the same time, if you don't allocate enough threads, then you need to add more threads on the fly. Anyway, there is a section in the textbook that talks about how we can set up a thread pool, but that's gonna be a ways away from now. But for now, what I want you to do is try out this Hello World program using pthreads. If you can't get it to work on your computer, then try it on a Unix system. So, Linux, for example. You can probably go up into the Jack Van Hall you can probably go up in Jack Ryan Hall, try it out on one of the terminals there, or possibly remotely access one of the Jack Ryan Hall computers and then try it then. What I want you to do is just try to get this to work. That's all. Yeah, I know you have your other programming assignments as well, but now we're moving on to the next chapter. So basically this whole class is looking at different ways of achieving parallel programs, because as you probably have noticed, there are many ways of writing parallel programs. Different APIs that are meant for different applications, different ways of achieving the same thing. Because, as you may have noticed, there isn't a one-size-fits-all model for parallel programming. So that's why we're looking at different ways of creating parallel programs. Yeah, we're looking at threads right now, but later on we're going to look at processes. That's what happens when we get into MPI. Anyway, that's going to be it from me for this week. Again, there were 3 parts to this video. The first one was assistance on how we can get our... The first one was assistance on how we can get our Darktro program to work. The second part was a preview on what to do for our midterm. And for this week, it's starting to look at pthreads. I do have another slideshow, but that's going to be for next week. But if you want a preview for that, I guess this is part 4 then. Again, we'll look into this in greater depth next week. But it's basically, hey, it's the same program, it's the same formula for our pi estimation program when we were looking at OpenMP. We're going to be trying out the same program, but instead of OpenMP, it's pthreads. I will spoil this. The program given to us in the book is intentionally incorrect, because what it is trying to show us is one of the things that can happen when we have multiple threads. It's one of these things that can happen when we have multi-threaded programs, and that is race conditions. When 2 or more processes, or threads in this case, race to the same slot in memory to write down something, only to be overwritten by some other thread. And as I may have mentioned before, in a race condition, last place wins. Because the last thread to write something will have that result be the one that sticks. And of course there are ways of fixing these race conditions, but if you don't fix these race conditions and they pop up in the weirdest places, the textbook calls these issues Heisenbugs, because they're named after the Heisenberg uncertainty principle, where the act of observing a system changes the state of the system. So yeah. Next week, so as I said, this week we're looking at the Hello World program. Try that out for yourself. And next week we're gonna be trying out this program that has a race condition in it, and then we're gonna see how we can fix that up. Right? That's gonna be it for this week. See you next week.